Everyone, so today we are going to be talking about gravitational potential energy. So we've already learned about gravitational potential energy on the Earth's surface. So if you recall, if I have an object on Earth with a mass of m and I lift it to a certain height h, the change in gravitational potential energy will be mass times acceleration of gravity, g, little g, times h, the height. Here we assume that we have a constant gravitational field, which is okay when we're at the surface of Earth. However, what happens when we move further away from the surface of Earth? Well, we need to come up with an absolute number on what the gravitational potential energy of an object is as we get farther and farther and farther away from the surface of Earth. So if we go back to Newton's universal law of gravitation, we know that the force of gravity is equal to big G, which is our constant, times m1 times m2 divided by our distance between those two things squared. So if we take this equation and we set it equal to the force of gravity equation, remember our force of gravity just equals mass times acceleration of gravity, and then we divide both sides by the mass of the object, we can get an equation for the acceleration of gravity as it's measured from Earth's or Earth's gravitational field. So we get the acceleration of gravity or the gravitational field is equal to big G, our constant, times big M, which is the mass of the planet. In this case, it's the mass of the Earth, divided by the distance from the center of the planet to wherever the object is squared. So this is a measure of the gravitational field produced by that large planet. Now, if we take this equation right here, we can see that the gravitational field isn't constant. So as we go away from the Earth, our R term gets larger and larger and larger. So since the denominator is increasing, that means the force of gravity or the gravitational field is decreasing. It's getting weaker as we move away from the Earth, or as the distance between the two masses get larger and larger and larger. So with this equation, we can come up with an equation for the absolute formula for gravitational potential energy. So if we look at our original formula for gravitational potential energy, we have mass, again, times acceleration of gravity, little g, times height. And then what we're going to do is we're going to take this whole thing here, which is equal to little g, and we're going to plug it into that little g there. Now there's one more piece of this puzzle, and this is the part where it gets kind of weird and a little confusing. So I'm going to try to take it step by step and really explain it as well as I can. We need a reference point, okay? And in this case, our reference point needs to be, where does the potential energy equal zero? So where in the universe does gravitational potential energy equal zero? Well, as our R term, or the distance between those two things, gets larger and larger, the gravitational field produced by that mass, the Earth, mass of the Earth, right, gets weaker and weaker and weaker. So it's approaching zero. Okay, so as R approaches infinity, then the force of gravity approaches zero. However, at the same time, the further the mass is from the Earth, the more potential energy it should have, right? Because height is increasing. So this is almost, it's like a juxtaposition here. So because of this, we actually put a negative in front of this equation, right? So here's our equation for that absolute equation for the gravitational potential energy. We get potential energy is equal to negative big G, which is our constant, 6.67 times 10 to the negative 11th, times big M, which is the mass of the planet. Usually we're talking about the mass of the Earth, but of course we could talk about mass of other planets causing a gravitational field, times little m, which is the mass of the object, divided by R, or the distance between the two things. Now, the reason we put a negative here is that, number one, gravitational potential energies are always going to be negative, but they get less negative the further out the mass gets. So as R increases, it's in the denominator. So as R increases, the magnitude of that whole number decreases. So the number, the potential energy, is getting less negative, and therefore it is increasing if we look at a number line. Now, on the other hand, as R approaches infinity, so as R increases, then we're also getting closer to zero. So our potential energy is approaching zero. So this satisfies both of our cases, even though it seems like a juxtaposition. Now here is a proof of the gravitational potential energy equation. So in your equation sheet, you're given this example or this equation here. So we have the change in energy is equal to the work done on the object, and that is going to be equal to the integral of the force with respect to r, so F dr. Now, the reason we have to use this equation is because the force of gravity is not constant as we get farther and farther away from Earth, right? The force of gravity is getting weaker and weaker and weaker as we get farther away. So suppose you are lifting an object from the surface of the Earth, which is a distance r from the center, as in like the radius of the Earth, right, to infinity. So we're lifting from the surface to infinity. And the work required to do this will be this equation here then, again, from your equation sheet. But here we have limits. So we're going from the radius of the Earth or the surface of the Earth to infinity. Now, in this case, Fr is the force of gravity, so we can plug that into the equation. All right, and we know that that's G times mm over r squared. And then here it's a negative because the force of gravity is down toward the center of the Earth, but we're lifting it up. So because the force is opposite the displacement, then we have a negative work done. So that's why there's a negative there. Now here we can factor out that big G times the mass of the Earth times the mass of the object because those are all constants. And so what we end up getting is the integral of 1 over r squared dr. So 1 over r squared is just r to the negative 2 power. So we add 1 to that exponent, which becomes negative 1, and then negative, right? We have to then divide by that negative 1. So we get a negative r to the negative 1, which is a negative 1 over r. Oh, my goodness, a lot of things there in my head. So the negatives cancel out, and we end up getting that gmm over r. Now here, again, we are evaluating this answer from r, which is our radius of the Earth, to infinity. So the final would be that infinity. So we get gmm over infinity minus gmm over r, because it's final minus initial. And then, of course, since we have infinity on the denominator there, that becomes 0, because as the denominator approaches infinity, then that whole term became 0. So what we end up getting here is just a negative gmm over r for our work. Now, if you recall, our change in potential energy is equal to the negative work done. And here, our change in potential energy, it's final potential energy minus initial potential energy. Final potential energy, of course, is the potential energy at infinity minus initial potential energy or potential energy at the surface of the Earth. That's going to be equal to work done. So here we just get 0 minus u equals negative work. And so therefore, our potential energy is equal to the work done on the object, which therefore is a negative gmm over r. So this is just proving that equation that I showed you on the last slide. All right, let's talk a little bit about language of this using this equation. So the potential energy given by this equation is a property of two particles rather than of either particle alone, because we have big M and we have little m. Now, there's no way to divide the potential energy and say that so much belongs to one particle and so much belongs to the other. However, because our Earth, or whatever big M, whatever planet we're talking about, because that mass is so much bigger than the mass of an object that is going to be moving around in that other, planet's gravitational field, as is true for Earth and a small mass, we often speak of, the potential energy of the baseball or that little mass. So we can do this because when the baseball moves in the vicinity of Earth, the change in potential energy of the baseball Earth system appears almost entirely as changes in the kinetic energy of the baseball. Now, if you have multiple particles in the system, then we consider each pair of particles in turn and calculate the gravitational potential energy of that pair as if the other particles were not there, and then we just algebraically sum the results. Potential energy is not a vector, so we wouldn't have to do this like a vector sum like we do with when we have multiple objects and we're looking at the force of gravity between all of these objects or something like that. We're just summing up the results of the different potential energies between the different masses. All right, another thing we have to talk about here is escape speed. So if we fire a projectile upwards, it will slow, stop momentarily, and then return back down to Earth, which we've seen a bunch of times, right, in our real lives. And we know from talking about, projectile motion and conservation of energy and all of that stuff before. However, there is a certain minimum initial speed that will cause it to move upward forever, theoretically coming to rest only at infinity. And we call this escape speed. So if we consider a projectile of mass m and it's leaving the surface of the planet or some other astronomical body or system with escape speed v, the projectile has a kinetic energy of 1/2 mv squared and a potential energy given by the equation that we just learned, negative gmm over r, where m is the mass of the planet, big M, and big R is the radius of the planet. Now, when the particle reaches infinity, it stops and has no kinetic energy. And at infinity, the particle also has no potential energy. So therefore, the kinetic energy plus potential energy, which is 1/2 mv squared plus a negative gmm over r, is equal to 0 at infinity. So solving this equation here for that velocity, we end up getting this equation. And the reason that we can use this right here is because we have a conservation of energy, right? This is our initial energy as we're escaping the surface of the planet. And then this is our final energy. So this is conservation of energy. Here, all we did was solve for v, which would be our escape speed. And what you end up getting for velocity or escape speed is equal to a square root of 2gm over r. Okay, so this equation looks very similar to just the velocity of a satellite equation, if it looks familiar to you, but there is a 2 in there, so you got to be careful with that. I would memorize this equation here. It's not on your equation sheet, but it is a very important equation to know, and it could come in handy on the AP test, so I would memorize that one. All right, one more thing to talk about. Let's talk about satellites, orbits, and energy. So we already know our potential energy equation. That is a negative gmm over r for potential energy. And then kinetic energy, what we're going to do here is we are going to set the force of gravity equation, Newton's universal law of gravitation, equal to centripetal force, because we know that the force of gravity in the case of a satellite is a centripetal force keeping that satellite in circular motion. So here we have these two equations equal to one another. And then we know kinetic energy is 1/2 mass times velocity squared. So here we can kind of see that happening here already. We have mass times velocity squared here, but we need to do a couple things to in order to make this look like this. So we have mass times velocity squared, so we need to cancel out this r term with this squared right here, and then also we need to multiply both sides of this equation by 1/2 in order to get that. So you get 1/2 mv squared for kinetic energy, and that is equal to gmm over 2r. So that's where that 1/2 went right there, 1/2 times r for kinetic energy. Now here, if we compare this equation here with our potential energy equation, we can see here we have 2r on the denominator, and here we only have 1r, and then of course potential energy is negative, and kinetic energy is positive. So what we end up getting here is that kinetic energy is equal to a negative potential energy divided by 2. Now, if we're looking at total energy of the system, we know that that's going to be kinetic energy plus potential energy. So if we insert those equations from the last slide, we get GMM over 2R minus GMM over R. And then, so what we end up getting for our total energy of the system is a negative GMM over 2R. Here, in order to find this equation, you would have to multiply this side by 2 over 2 in order to get a common denominator between the two. So if we see this, we know kinetic energy is GMM over 2R. So this is just energy is equal to negative kinetic energy. So this is an equation that you can use when you are solving for the total energy of the system. Of course, it does depend on what exactly you're given. Here, the total energy is going to be constant unless you have any external forces acting on the system. And the system in this case is like the mass of the Earth and the mass of the object or whatever. So if there are external forces, something moving the mass off the surface of the Earth or something like that, then conservation of energy does not hold. But if you don't have any external forces, you can say that initial energy is equal to total energy. Of course, like I said, it does depend on what you're given in these problems. Now, this last equation that I have here, this negative GMM over 2A, in this case, A is the semi-major axis of the elliptical shape of the orbit of the satellite, meaning just the largest axis. We'll talk a little bit more about elliptical orbits in the Kepler's law lecture, but for now, just use R for A. For the most part, we can just assume that satellites are orbiting in circular motion.